Good morning, everyone.
Yeah.
As I mentioned, I will start today on some basic introduction, but also which also includes some exercises on the design of civil structures, components, civil works. And by civil works, I basically mean the headworks, the conveyance system, the headrest, canal or pipe, the weir, the intake, the forebay, the settling basins. So today I will start that. If I'm not able to finish all the components today, I will extend that a little bit on Friday, coming Friday, where I will then move on to, after I finish the civil components, I will move on to the electromechanical, the selection of turbines and generators. So today's content, I would just like to start from a quick review of the previous lecture, just take a few minutes just to get back to our session. Then I will talk a little bit about how to design the intake, the diversion works, the headrest canal or pipe, the gravel trap, settling basin, and forebay. It will be a little technical, so please, if you have any questions, and if I'm going fast, please stop me, and I will try to explain. I will also provide some examples, and also actually I will provide a few Excel templates where you can practice. There are some, the different functions are explained in the template, but you may need to consult some reference materials also. But I will try to walk over and I will try to give some hands-on exercise also. Okay, as far as review of the last class lecture was concerned, I actually wanted to just a moment, I put this out here. I wanted to just make a review of the flow duration curve, because as you know, the flow duration curve is an important design computation for any hydropower projects. And basically, as I explained earlier, the flow duration curve is, just a moment, I put it back here again. The flow duration curve basically tells you what is the variation of discharge in the river over the year. So, for example, like here, the minimum flow is available 100% of the time. And there are about 80% of the time, about 3.5. If you really zoom this, you can see that 3.5 cubic meter is available 80% of the time. So 80% of the time, the flow is 3.5 or above. 60% of the time, it is 5.5 or above. 20% of the time, it is 18.6 or above. 10%, 31.9 and above. So 95% of the time, what you call the firm flow is around 1.9. So now we have to select what should be our design discharge. Do you want to design our hydropower project with the capacity available 95% of the time? Or you want to design for a larger capacity using the design discharge of 5.5, but it will be available only 60% of the time. Rest around about 40% of the time, it will generate less than the full capacity. Now, some projects are designed for 40% exceedance probability, designed for 9.8 cubic meter per second, but only 40% of the time you have the capacity where you can generate at full capacity. 60% of the time you will have to generate lower than the full capacity. So this is the decision. Selection of the optimal design discharge is a decision that a designer or planner has to make. Now, what is the basis for this decision? Now, you have to be careful that if you design for 95% dependable flow, that means you will get a constant generation at full capacity almost 100% of the time. So if your demand is the same as the installed capacity, you are assured that you will get demand, you can meet the demand 100% of the time. But if you design for lower dependable flow or higher capacity, the generation will not be available full time. So in the last lecture, we prepared the flow duration curve for one example. So today, I just want to give you, I actually showed this graph some time back also, but I just want to repeat it now. What I want to say is, like I mentioned, the power calculation, this question mark actually somehow changed. It is efficiency times gamma, the specific discharge, times Q times H, which is given in kilowatt if you use gamma. So this is your formula to calculate the capacity. So suppose we have one power plant with 20 meter net head. Now, if you design for Q90 at 2.5 cubic meter per second, you will get 417. So this red line, 90% of the time you get 417. Okay. Now, if you design for 5.5, you get 60% of the time you get the yellow one, you get for 916 kilowatt, but after that your power capacity decreases. Okay. Similarly, you could also design for, because 40% of the time you have 9.8 also, you can design this same project for 1.638 megawatt. But again, as I mentioned, the power duration will be given by this white line. Okay. So now, if it is an isolated mini grid or isolated project, you will have a problem to match the supply and demand if you design for 40% or 60% dependable thing. So, but if it is grid connected, what you could do is any surplus, you could, for example, maybe let's say your like a fixed demand in that thing is around 420 kilowatt. So what you could do is you could design for 1.6. So you could sell the excess energy to the grid or to another supply. Of course, you have to have agreement, a power purchase agreement to sell it. Okay, but in a big, large system, in a national grid, you also have thermal generation. So what you could do is you could displace thermal energy when you have more than your need. So the optimization of hydropower in micro hydro, mini hydro, which are isolated, I mean, you tend to design for high dependable flow. But if it is grid connected and if you have other sources of energy like thermal, then you could really do an optimal operation to get the maximum benefit from your project. So I just wanted to mention this a little bit today so that we get the feeling of how the basis for selecting the design discharge or the design install capacity of hydropower projects. You see, so the variation in flow is important, but you have the option of sizing your power plant at various dependable flow. Of course, this is for a purely run-of-the-river project. If you have a storage project, then this flow duration curve will be, regulated. If you regulate, then you could transfer, you could store part of this water here and then use it to regulate and generate at equal capacity throughout the year. But for run-of-the-river project where regulation is not possible, this is the type of power duration curve you will get. So I just wanted to bring that up. Is there any question on that? I mean, if there is, if there's no question, I will move on to the civil works part.
Caros colegas, haverá alguma pergunta em relação à matéria dada?
Yeah, sorry. Thank you, Divas. Just a quick question. If you go back to the other slide on where you show the exceedance table, please go back on your slides.
Yes, this one?
Yeah, that one. That one. Yeah. Let's assume that we are designing a project, right?
Yes.
No, not that one. Please, can you go back? Who's moving the slides?
I am actually.
Okay. Okay. Can you go back to the slide that you had before?
Okay, just a moment. Do you mean just a moment? I don't know, today the computer is a little slow on my part also. Okay, this one, sorry.
Yeah, this one. No, the next one.
Yeah. Oh, what happened? Sorry.
Next one.
Sorry, yes, now it's here.
Oh. Not this one. Yeah, no, not this one. Yeah, this one.
Okay, yes.
Yeah. How do you go about the design of the oh, it's moving. It's moving automatically?
No, it's there. No, it should not. It should be the same. The slide should be the same.
Yeah, it is the same, but it's not the same. I want to go back to the kilowatt potential.
Do you want the power? There are two slides.
Yes, power. That's the one that you showed before, yeah.
Okay, this one probably, right?
Yeah, this one. Keep it that way. Yeah.
Yes.
Because we'll talk about this one.
Yes.
Yeah. Let's imagine that you have a project, huh? And you can go either way, and you have to choose the design of the cap kilowatts or whatever you want to do as your criteria.
Yes.
What is acceptable in terms of the flow, dependable flow? Do you go usually for 90% and above, or you can design for 60%?
Yes, thank you. That is a very good question. Actually, this will depend on 2 or 3 things. One thing is if it is an isolated system, okay, and your only source of power is this hydroelectric project, so you want then you may need to go for higher dependable flow like 290 or 95 if it is isolated, because you want to meet the demand is, so you have to size your project according to the demand. Let's say, so this project can meet a demand of 417 kilowatt throughout the year, more or less. Okay, that is the case. But if the project is connected to the national grid, or if the mini grid is a hybrid, okay, for example, your demand load may be 900 kilowatt, okay, throughout the year. Let's say 12 months, you have 900 kilowatt. But if there is only one option for this hydropower, if you design for Q90, you will get only 417. So you will not meet the demand anytime in the year. But if you have a demand of 916, you design this project for 5.5, 916 kilowatt. So 60% of the time, this project can meet your demand. Another 40% of the time, what you can do is, I mean, you may have, maybe you import from neighboring grid or use another source like thermal. So you have combination of hydro and thermal. So when you have enough water, you generate hydro, because hydro operation cost is negligible. Then when you don't have water, when the demand cannot be met, you generate some thermal. So if you design for 916, 60% of the time it can meet 916. 40% of the time, this area, this portion here, this energy has to be, power has to be met by another source. That is another option. But if it is in the national grid, if you can connect this project to EDM national grid, because from what I understand, EDM has, like, I think now you have thermal generation also. So you could design this project for 40% dependable, and then you displace thermal energy when you have hydro. So that will give you I mean, it will avoid the cost of thermal generation. So, but this depends on the optimization. I mean, so it depends on the cost of for 417, designing for 417, designing for 916, designing for 1638. You need to get the cost and you need to get the benefit. If you have the option of selling any surplus energy, then designing for higher capacity would be optimal. For example, in my country, Nepal, if you are designing a project and you connect to the hydropower, national grid, most of the projects now are designed for Q40, for higher capacity. And now if you have because you have Kohora, Basa, the reservoir project also, what this does is you basically generate 1638 for 40% of the time, and other time when the water is not available, flow is not available, you cannot generate full capacity, then you can use generation from storage project. So combination of run of the river and storage, when you have a combination, a mix of storage and run of the river project, you can design for Q40. Now, in my country nowadays, there are new projects, run of the river projects, which are designed for even Q30, Q20. Also, you can have a small pondage, what we call peaking ROR. So you can store water for 1 day, for within 1 day, 16 hours like that. So what you do is you store the water in one day, and if you don't have, your full capacity is 1638, but you don't have water. Suppose you have only 2.5 cubic meter, okay? Because when you sometimes 95 over here, when you are here, you have only 2.5 cubic meter. So if you generate throughout the day, you can generate only 417. But if you can store this water for some hours, 12 hours, 16 hours, then you store water, then you generate for 6 hours, 8 hours, you generate full capacity. Because the load curve is such that in the morning, in the evening, you have peak, especially in the national grid. So morning and evening, you generate more. Other time, you generate less. But to do that, you have to have some pondes, some storage in that in the behind the weir. So this is an optimal.
Thank you very well. Yeah, I understood it very well. Thank you for the explanation.
Yeah, thank you so much. Thank you for the question also. Yeah. Okay, so I think now let us move to the agenda of today. Basically, I will start, like as I showed, this is basically in terms of civil works. You have the headworks, you have the weir, you have the intake. There are different types of intake: side intake, drop intake, frontal intake. So is there? Then you have what is known as a gravel trap, just a little bit downstream, a little bit away from the intake. Then from here, you have the descending basin. Okay? So gravel trap will trap the small gravels and other things that passes the coarse trash track. Then the other final sediment is settled in the desilting basin or descending basin. Then you have a canal or a pipe that brings the water, and you go to the forebay. And from the forebay, you have the penstock that takes water from the forebay to the powerhouse. So this is the overall scheme of a typical mini or micro hydro project. Okay, and the civil works are the diversion work, the intake, the gravel tap, the headrest canal or pipe, forebay, desilting basin are considered civil works. Penstock also has anchors and saddle blocks. These are civil works where you use cement, sand, reinforcement, and stones. But penstock can be steel pipes or high density polythene pipes also. So and the tail race canal is after the powerhouse. You have the tail race canal, so which also is basically has to be designed. And for civil works design, the basic principle is hydraulics. No? Hydraulics is the study of fluids, no? And we are talking of water. And basically, I did cover, it's basically the water pressure and the head and the losses, the hydraulic losses, the hydraulic head has to be, because you are basically the potential energy of this, the water that comes here goes to the forebay, and for the water to be taken from the diversion point to the forebay, you need a canal or a pipe where there is a hydraulic gradient. So you have to use the gravity flow. Okay, what is known as the gravity, the level difference between the intake and the forebay. And then you have the pipes and other things that will take you to the forebay. From the forebay, of course, you want to have the minimum difference between forebay and the weir, because from the actual power generation is from the elevation difference from the forebay to the powerhouse. This is important. So I will just now talk about the diversion weir and intake and the river training and flood protection works in the river. As you see, as you must have seen if you go to a irrigation project or a hydropower project where you have a weir, okay? This is the weir. So there is over here, this is the river is flowing this way. So you have a weir, you have an obstruction, you raise the water, then the water is, the intake is here, the intake passes, the water is conveyed through here. But now you have to have the protection of the flood walls here on the right side and the left side, because you are going to raise, this is the natural river is slightly changed because you raise by a weir or something, raise the water level so that the water can pass through the intake. So you have to have some river training works on the river, because once you raise, the water will also flow here. Okay, so there is the flood level slightly increases. And these are the gabions protection. These are the river training works, because when you have flow coming here, you want to protect your river banks. So this is basically the diversion weir, intake, river training, and flood protection work. So if you are a design engineer, you have to design size, the weir, the flood wall, the river training protection, the gabion protection, the intake, so that the water passes through the intake and you can divert your required amount flow, okay, cubic meter per second. You can divert according to the design discharge, you can divert in the conveyance system. So basically the key conditions, design conditions you have to follow. I may have talked about it earlier also, but since we are now in the design phase, so we want to make sure that when the water in the river is available, we want to divert the design flow in the intake. So what should be the water level? How much should the water level be raised so that the flow that we want is coming to the headdress canal? Also, we want to make sure that, because in the river, there are sediments, there are bed loads, and there are floating objects, there are suspended sediments. So we also want to minimize, make sure that the sediment does not come with the water. So we want to minimize the entry of sediment. Also, we want to make sure when there is a flood, we don't want too much of water coming to the canal, okay? Because when the water level rises, then the flow will also enter your conveyance system. But because we don't want to divert too much of water also. Also, we want to make sure that by having these flood walls, we want to protect when there is a high flood, we want to protect our structures and adjacent land from flooding. Okay, so that is also important. Another thing, I mean, for mini, micro, the environmental concerns are, as I mentioned, are limited, but for small, medium, and large hydros, the environmental issues are also very important. So when you make a obstruction here, the weir here, you see, the fish cannot move from downstream to upstream, mainly. From upstream to downstream, when the flood water is there, it can just jump, the flood water will flow above the weir. But from downstream, normally it is difficult for the fish to move upstream. So in a medium large, you have what is known as a fish ladder in some portion over here, where you have a longer route of the, you sort of control the velocity of the flow from upstream to downstream, so that the fish can also pass from downstream to upstream. So this is sometimes known as fish passage or fish ladder. It's not shown here, but if you have a diversion weir or a barrage or a dam, you have to make provisions for fish to pass from downstream to upstream. This will not be covered here, but I think you should be aware of such a situation. Okay, so now basically I'm just showing you just to give you a sort of review of the civil structures. Okay, the BB, this is the cross section here. If you see here, the weir is something, you have a stone masonry temporary weir. So what you do is you just raise the height of the bed level is raised by H thing, and you have a crest. So you have to design here. Now, how much of water passes over here and how it passes is a design consideration, which I will cover here. And CC is the, with a permanent, and this is the temporary wear. With a permanent wear, you have a basically RCC concrete thing with some, on the top, you have the reinforced concrete layer 1.1. So this is the ratio of sand, gravel, and cement. Okay? And you have a stone masonry here. So this is the size. This is the shape of the wear. It's just the wear is an is used to raise the water. Okay, and the cross section of AA here. This is the intake portion here. The intake portion will have, if you look at it from here, if you cut this here to here, this is the intake thing. So you have what is known as the normal water level is the crest water level. The flood water level is here. This is the small orifice here. So, and this is a trash rack, and the water will enter from the trash rack, pass through this orifice and opening. Then it will go to what, I mean, the gravel trap is nearby. So it will go to a gravel trap, and the gravels are flushed out periodically, and the slightly clean water then goes to the canal. Okay, and this is in the canal. At some point you have the spillway also. So you want to control the level of depth of water in the canal. Any extra additional flow more than required for energy, for power generation, just will be spilled from this section. So when you design our diversion weir and side intake, what we have to do is we have to design this weir. I mean, basically design basically the crest, the thing. And when you say design the weir, we have to make sure that the water, by raising this height of this, the level of this water, the water can, because what basically it does is the normal river level will be according to the crest level. And based on that, we will divert the design discharge through the side intake over here. Okay, so now the height of this weir is designed according to that. Similarly, when there is flood water, it passes through here. So we have to know what will be the level of design flood. Okay, so like for example, a flood that occurs once in 20 years, to what level will the water rise? Because if the water rises above the flood, the wall of the river bank or the wall of the river, the flood wall, then it will go to the adjacent land. And on the right side, in this case, it will go to the conveyance, the canal, and other thing, which will not be good for the system. Okay, so basically this is the diversion, and I'll show you. I'll talk about the design aspects a little bit. So now I just diversion weir are, I think I explained that a little bit earlier also. There are three types: temporary, semi-permanent, and permanent. No, as I mentioned earlier, I think when I did the introduction of the civil works, for micro hydro, for 5/10, very small micro hydro, it's basically temporary. These temporary are made from just boulder materials, some stones and branches of trees. And every year during flood time, this is washed away. Where there are not much of boulders or something, you can also have a gabion weir, okay? Where gabions, as you know, weirs are wire mesh, where you sort of fill them with small stones and then make it like this, and you just rose the thing, and there's a backwater. The water will basically, you have on the top, you could have some PCC, plain cement, concrete lining on the top, just to protect from scouring or something. When when there are not, when the rivers do not carry too much of boulders, this is fine. But if it carries too much of boulders, this semi-permanent will not work. The gab and wear will not really work. So, but for a permanent wear, especially used for when you have small, medium, and large hydros, basically this is the permanent. They use high grade concrete, and for large dams, they also use what is known as the roller compacted concrete, RCC. And over here on this side, this is actually, this section is called the undersluice. The undersluice section is normally gated. You have a small gate. You can sort of control the flow of the water in the gate. So this is the bed. The invert level of the undersluice level is just around the bed level. So the water is sort of diverted to a side. On this side is the intake. So over here you have the intake, and the water will go over here. So this is basically a low height concrete weir with an undersluice and a side intake over here. This is just an example from a hydropower project. So now the main important formula, this is for in open channel hydraulics. This is a very I would not say popular, but it's a very simple formula where when you have a weir, or like if you have a small obstruction, then how much of water discharge will flow over this here. Suppose over here you have no, I did not. Okay, so when there is a when the like for example, when the water level, it's, let's say, at this level, okay, over here level, how much of water will flow over the weir is a question that we have to where is a value that we need to know. So what it tells you is, this is a simple equation, which is the Q, the discharge over the weir, over the here, is equal to the wear coefficient, and this wear coefficient depends on if you have a broad sharp edges like this, where the wear coefficient is 1.5. If you have rounded edges, it's 1.6. If you have rounded overall, it's 2.1, so you can pass more. Sharp edges 1.9, rounded 2.2, roof shape 2.3. So based on this shape of the wear, the wear coefficient is given, and the length of the wear is how wide is the wear, is the length in meters, and the overtop is actually, it should be head over the wear. What is the water level above the top of the crest? So this portion is the head. So if you want to calculate the water level for any given discharge, a flood value, you just use this formula, with where overtopping would be Q divided by, on the other side, C divided by CW divided by LW, and to the power, it's the inverse of this. This is 3.2, this is 2.3. So this is the basic formula used to calculate the flow passing over the weir at what elevation. Okay, so if you know the elevation overtopping, I mean the head over this thing, you know how much of water can pass here. If you know the water level, you can also estimate the discharge that will pass here. Okay, so for a given discharge, you want to know what is the water level. So this is a very simple but a very useful formula to be used. Okay, and now just to give you an example, so this, okay, this one is the wear crest. Okay, so when I say the H over top, okay, the H over top is, if the water level is here, this is the head of the overtop. Okay, so now if the water level so you want to, there is an exercise I want to give you. Now, a broad crested weir, 1.4 meter high, okay, this is 1.4 meter high is from here, and 20 meter wide has been placed across the river. Okay, this is 20 meter, its height is 10. And the design flood is 75 cubic meter. What should the height of the flood wall above the weir at the river bank be to contain the flood within the river? So now you want to make the flood wall on the left side and the right side. Okay, this is just the weir, and like I showed here, okay, here. So this is the flood wall. Okay, this is the plan, okay, and this is the section here. Okay, so you know that the flood value is 75 cubic meter per second. But so when the flood value is 75 cubic meter per second, if a 75 cubic meter of flow passes through here, what would be the water level above the crest of the above above the crest, so that so how high should the flood wall be is your design decision. So now I would just like to ask you, as I showed here, let me also explain this. This is very important. This is the weir, and I talked about the undersluice here earlier. Okay, this is the undersluice. I also talked about the fish ladder. This fish ladder is basically that to let fish pass here, because you have the weir here, but this fish ladder is like in some section of the weir you have sort of a long passes where you control the velocity, and this side is the intake and the intake canal and the flushing system and other things. Okay, so this is the crest wall. So now the question is, you want to pass 75 cubic meter per second flood over here, and now you want to know what should be the height of your flood wall. You want to know the height of this flood wall from the top of the crest. So now, can anybody guess, or sorry, not guess, can anybody tell me what should be the procedure? Okay, I just give, of course, you have to do some calculations. I just gave you 3 options: 15 meter, 20 meter, and 25 meter. What do you think? And you can take, okay, just to, help you. These are the 2 formula you have. Okay, Q is equal to this one. And then using this formula on the other side, you know Q. So you know LW, which is 20 meter. And this is broad crested weir. So broad crested round edges, let's say this one, the CW is 1.6. So can anybody tell me what would be the height of the flood wall above the weir crest level? Yeah, anybody want to try?
Sim, colegas, alguém quererá tentar resolver o exercício? A pergunta é qual deve ser a altura da parede inundada nas condições em que são colocadas. As condições são de que temos a represa, portanto, da açude é 1.4 de altura, 20 metros de largura, e esse açude é colocado, portanto, no rio. E é exatamente a parede de inundação desse açude que nós temos que ver qual deve ser a altura. Queremos que o rio tenha um fluxo de 75 metros cúbicos por segundo. Conhecemos a altura da SUD. Yeah.
Yeah. Okay. Let me just, as I mentioned, this was like you basically first you know Q. Okay. The Q is given as 75. So basically, you need to calculate what will be the flood water level for Q75. Okay. So basically, you have to use this formula. See, because uh, the 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 H over top, the head over the weir for given discharge of 75 will be, let me just show you, the head over the weir is over top is Q divided by CW times LW to the power 0.667. Okay, this one over here. So it's a very simple thing. So H over top is you have 75, CW is 1.6, and length of the weir over here is 20 to the power 0.667, which is actually equal to 1.76. So H over top is 1.76. But we want to add, I just say, the question also gave you freeboard of 0.4 because there will be some fluctuation of water because of the way it's a small pond is, so you don't need a very large freeboard. So basically, if you add 0.4, then if you make the flood wall 2 meter high, then this can easily pass the flood discharge of 75 cubic meter per second. But if you make the flood wall lower than 2 meter or something, then it will basically enter, water will flow on the banks of the river, and because these are the original ground level was here, there is compacted backfill, and it can cause some impact damages to your structures on this side. So I just wanted to show you that whenever you you disturb, I mean, this is the river, whenever you build a structure in the river, it will disturb the river. So disturb in the sense it will change the hydraulics, it changes the way water flows. So the water level will change. So, but when you have a weir, you can calculate exactly what will be the water level when you know the discharge. So this is one example, one common, I mean, method used to design your flood walls. So you want to make sure the adjacent area is not flooded. Similarly, like in Majau mini hydro, I understand that in 2015 flood damaged the powerhouse. So we should estimate what was the flood at that time and what was the condition in the river. So what was the water level during that flood time? Of course, that is not exactly, probably it was not exactly a weir situation. It was in the tail race section. So your powerhouse should be above the flood water level. So it's also a calculation that we have to do when you design your location, your siting of the powerhouse. Okay. So, so this is just one example of designing the flood protection in the area. So when you are designing a weir, you have to now the location, the height of the crest, the undersluice, the side intake, and the flood wall. So, any question or? Okay. So anyway, so this is the one of the yeah. So this is just one example of how a flood wall is designed. Okay. Now I will move to similarly. Again, will be in civil works. There'll be a lot of equations and formula from hydraulics that will be used. Okay, so similarly, as I mentioned, you have to design. Now you want to make intake here. Now you have to design the trash rack. What should be the size of this trash rack and this angle? What should be the opening, okay, of this side intake, okay? And what should be the water level here? What is the water level here? How much of the flood design flood level? All this calculation, okay, is part of the civil component design. So similarly, there is an opening here, like for example, here, okay, here, like this same drawing, there's an opening here. I know this is the same one. Okay, yeah. So basically, now from a civil component design, you have to now sort of design involves calculating computing the flood level, the normal river level, the canal level, this size of the opening, what should be the height of this opening, what should be the width of this opening, what should be the trash rack openings and other things is an important design parameter. And like the flow through above the weir, we use this formula which was given earlier. Now, the water that flows in the orifice, and what we call this is a submerged flow. Submerged in the sense, this opening is submerged on the upstream side and the downstream side also. So basically, on the downstream side also, it's submerged. In the upstream side also, it is submerged. Now you have to calculate the flow that passes through this one, because now what you want to do, you want to pass the design flow from this opening. So you have to design this opening, and the formula we used here is Q is the discharge in cubic meter per second, area is the opening in meter square, the width and the height, and C is the coefficient of orifice depending on the shape. And for roughly finished sharp edge concrete or machined structure, it is 0.6. For carefully finished, it is 0.8. Just an opening there. And G is 9.81 meter per second square, the acceleration due to gravity. And water level at the river is HR, normal water level. And water level at the headrest canal is HH. And this difference, HR minus HH, is the head difference between the upstream water level and downstream canal level. And based on this formula, basically 8C square root of 2G and the head difference between upstream HR minus HH, you can calculate the Q. So when you know Q, because we know the design discharge we want to pass through here, we basically then make the opening, the size of the hole, let's say the orifice is designed with using the area given here, okay? And normal water level is basically the weir height, okay, as showed earlier. And orifice opening should be designed as per normal water level, an additional 5.5 to 10% design flow to account for head loss at the trash rack. So there will be some head loss here. Submerged flow conditions ensures that excess flow does not enter. When you have submerged flow, it's good that it doesn't, that you can, it's a control. You can use this formula to derive it. Excess flow, whatever extra flow that flows above the design discharge has to be spilled back to the spillway. So basically, the problem is to design the opening here, and you know the QD, you know the crest level, then you want to basically find the size of this opening. Okay. Now I have a small example. Okay. Now what it is saying is, suppose you want to design this opening to pass 400 liter per second here, and the normal river level is 9.9 meter above bed level, datum. Okay, the estimate flood level is 2.1 meter above the riverbed. So 1 in 20 years, the flood will come here, and the size above the river level, and you have to also size the spillway to spill whatever. So what happens is, in normal level, you want to divert 400 liter per second, but in high flood level, it will divert more than 400 liter per second, which has to be spilled or sent back to the river later. Okay, so now, and the orifice design is made in such a way, there is a slight, the orifice, the invert level of the orifice is normally about 0.2 meter above here, and the orifice size is 1.5 meter. The head is the opening is about 0.4, which we'll calculate. This is the normal water level, the flood level. Okay, and basically, like we did for the flow in the weir, we also need to use this formula to calculate the opening size and how much of water will flow. So I think we are a little bit around 50 past our time. So let me stop, take a 10-minute break now. Then then we'll talk about this exercise after we come back for a 10-minute break. Dr. Carlos, is that okay?
Yes, I think we can have 10 minutes break. Yes, it's okay.
And so that you can also think about this. So as I mentioned, this is the formula we have to use. So please think about this example also. Yeah. So Carlos, we'll have just a 10-minute break. Okay.
Okay. Thank you. 10 minutes break. Thank you very much.
Okay. So the solution to this design problem, orifice design problem, is we want to know the size of this opening here. So we want to know the size of this opening here, and we know, and we want to pass minimum of 400 liter, but we want to make sure that this has the capacity to pass 15% more. So our design capacity for this orifice is, we want to fix it to 0.46 cubic meter per second. And now we have to restrict. Normally the velocity over here is, I think you can bring it up to 1.2 or 1.3 meter per second, but not so high. Maybe if you have because if you have a high flow, then it will also bring in a lot of boulders and other materials, and also it will damage the structures here. So basically, we need to, if you want to get this around 1.1, so we want to get an area of 0.42 square meter, because we will divide Q by V gives you the area 0.42. And if you set the orifice height to 0.4, then we get the width of 1.1 as we showed here. The 1.1 is the width of the orifice. The height of the orifice is 0.4. And based on that, we need to now check what will be the capacity of this, the water that will flow here. So we use this formula, which is given by the discharge that will pass through the orifice, which is discharge through the orifice formula is used here. Based on that, we get a discharge of 0.52, which is okay. And we check the velocity, which is also 1.23, which is okay. Now, so basically, it's a simple thing. We want to design this orifice to pass a minimum of around 0.46 cubic meter per second. But now when the water level is 2.1, how much will pass here is also important. And now during the flood time, the water level increased 2.1 and the downstream is 0.7. So there is a flood will around 1.38 cubic meter per second of water will pass. It will pass more than the design requirement. So any additional water, this additional water, the 1.38 cubic meter per second, because our design discharge is only 0.4, 0.46. So additional water has to be spilled from the canal on the other side. Okay, so this is a very simple, I just give you an example. Now I will introduce you to actually a design manual, which is more detailed. Okay, and I will just share this in the Zoom, through the Zoom session. I think I can share through, okay, I think I can share it through chat, or I will send you by email otherwise. I will just attach one file. Just give me a minute. I should have done it earlier, but yeah, I thought I would do it here, 26 exercise. Okay. Okay, so I think there is some problem with sending. Let me just, I will just give me a minute. I will send the file through email. Okay, then you can, let me just pause the share or stop the share. I will just stop the share, and I will send you one Excel file by email in the same email that Dr. Carlos sent you today's presentation. Just give me a minute. Okay, I've sent you that thing, but I will now share that here also. Uh, can you see my screen? Yes, I think you do. Okay. I just shared with you uh, a template where there's an Excel file where there are different sheets on design of side intake, bottom intake, headrest canal, headrest pipe, and settling basin. Okay, and these are basically you need to enter. This is just a sample thing. You need to basically enter in the input the ones marked with the blue, okay, and like trash track coefficient, what type of trash track you want, flat, rounded, it will have a different coefficient. What is the trash track thickness? What is the spacing of this trash track? What is the velocity, approach velocity? All these things. The blue ones are you need to enter, and the other are automatically calculated. So basically, and in the this one actually, I will. This is based on an micro hydro project, a mini hydro project design manual prepared under ZIZ for Nepal. So it's basically a case for Nepal, and this was prepared by a colleague of mine, a friend of mine, or I mean somebody I know, acquaintance, and he and his other colleagues, that friends of mine have prepared this. And if you go to these, some of these, I actually just selected some sheets for now. The manual covers turbine and other things also, but today I just sent you the sheets related to civil works, but later on I'll be happy to share with you the whole thing. But it is slightly designed for the conditions in Nepal. So there are some modifications that needs to be made, especially in terms of hydrological parameter estimation. But these templates will help you design side intake, bottom intake, how a bottom, and these are, and the reference I provide at the end of my presentation slides also shows the textbooks and other technical books that will help you explain the principles and the formula used for this intake. So similarly, for bottom intake is here, for the headrest canal, it's here, for the headrest pipe, it's here, for the settling basin design, it is here. And some of these are quite technical. So it will be difficult for you to understand in the first instance, but if you are interested, I can discuss with you separately. You can contact me. I can provide you the manuals and other reference books that will help you to understand better, because these are, I mean, of course, to design this, you need a long-term capacity building, training, lecture, classes to be able to understand each of these. But the objective of my presentation today and in this session next time also is to give you an idea on what type of design that will be necessary at the pre-feasibility or a feasibility level. Because with this design, then you can estimate the cost of these components, which can be used to do the technical feasibility as well as the financial and economic feasibility of the project. Okay, so I have shared this just now through email, in the same email that Dr. Carlos sent you the presentation today. If you do not receive it, let me know. I can send it to you again. Please send me an email or let Dr. Carlos know. We will send it to you again. So in your free time, I don't know, maybe during within this hour, it might be difficult for me to explain each step of this, but I will. I hope you during at home you can have a look at these Excel sheets and let me know if you have any questions. Okay, but just to give you an example, just explaining the same Excel sheet the side intake design, I mean, you see there is a flow chart is presented here, and basically it gives you the orifice parameters that needs to be like you see the HR, the opening, the HRHC, like we did just earlier. I just showed you a very simple example to show you the steps, but this has to be, I mean, for a real design, there are more steps than that, which is given in the Excel template. So this is basically, as I mentioned earlier, that during the flood, when the water level is high, during normal water level, the discharge that passes through the canal is the design discharge. Your discharge you want to take to the forebay to use to generate electricity from the powerhouse. But during the flood season, this opening, the orifice will also pass more water, no? Because you see, our requirement was 0.46, but during flood it passes 1.38. So we need to then downstream the canal, we have to make a spillway. We have to, any excess water, we need to pass it back to the river. So basically, we need to calculate the canal and the spillway thing. And the river flood conditions, we also calculate. And this is basically, now based on this, we basically calculate the trash rack also. Okay, this is the this is the spillway, and the other thing we calculate in the orifice, the intake, how much water passes in normal water level. You should pass the design flow. In high water level, it passes more than the design flow. So any extra, you have to again spill it. You know, like if you I go back here. I think my over here. So you have during normal water, design flow is passed here, which is 10-15% is used, so that just to for seepage and also to flush some water, the gravel and through the gravel trap. But during the flood time, more water flows, like 1.36 flows. So this water has to be passed through the spillway in the canal. So the normal water of the canal is here. So any additional water more than the design flow is passed through the length of this spillway. So we have to design the length of this spillway downstream. So this is a design parameter also, which is basically this flow chart will tell you how to design. And if you go to the Excel sheet, the exercise that I showed here, okay, this one is, you have the trash rack calculation. I'll show again the orifice calculation, which is shown here, and then what will be the length of the spillway requirement, because during flood time you divert more water. So all these things will be it is automatically, once you give this, it is automatically calculated in this Excel sheet. Okay, so which it's in the Excel sheet, in the comment it is explained, but you have to consider, I mean, if you look at it here, the formulae is also given here, but you may need to consult some reference technical books also. So this was for the side intake. Similarly, you have the trash rack. Okay, the trash rack has to be designed in a way, you have to say what should be the opening of the trash rack, and then what should be the spacing of the trash, I mean, based on the spacing and the material used for the trash rack, you basically, and also one thing you estimate here is what is the loss. Okay, there is a basically there's a loss of there's a head thing, so you have to basically also calculate the head loss of the thing, so that you basically what is known as the basically it's basically for designing of the trash rack. I think just to mention that. And these are the steps that is given here. Okay, and so I encourage you to look at these to play with this Excel sheet. Maybe you focus on the intake. I did not. You can look at the bottom intake also, but I would ask you to focus on the side intake. For example, I will just show you. This is it just gives you an example. This gives you the example of the trash rack calculation. Okay, and other thing. For example, okay, now for trash rack calculation, what we are doing is we are assuming there are different type of trash rack. Okay, over here shown here, flat, rounded front like this, tipped back, both end rounded. Okay, no trash rack. If you do no trash rack, then there is no, for example, there is no trash rack coefficient. There's no loss in the thing, because there is no obstruction. But normally you need to use a trash rack. Suppose you use a flat trash rack, then you get a 2.5 thing. So now basically it also tells you what in the input, what are the bar thickness. Okay, this MHP GL means the MHP guideline says it should normally be from 5 millimeter to 5 millimeter width to 40 millimeter depth, to 5 to 75 millimeter depth, and the spacing is normally less than 75 millimeter. The approach velocity is basically the trash rack in general. In the trash rack, you want to put about 0.5 to 7.5 meter per second. You can go up to 1 meter per second also. And approach, this is the approach velocity. The angle of inclination, it's basically this angle of inclination of trash rack, the beta is basically 60 to, it gives you here 60 to, angle phi, it gives you from 60 to 80. Then flow deviation, like with respect to normal, if there is a bend or something, it's a beta. Normally there's no flow. I mean, if you do a slanted thing, then you have this beta degree. What is the design discharge? As I showed earlier, if you want to get a 460 liter per second, you put it here. Height of the trash rack, bottom, this height of the trash rack, this is 0.2 like we did here. So head loss due to friction. So you use the formula which is given here, the head loss due to friction. If you look at the head loss, head loss friction, this is based on KT over, this is the formula that is used here, and based on this trash rack schematic diagram. Okay, so this is the formula used here. Head loss, so head loss coefficient K, head loss due to bend, head loss HF is the head loss, the total friction thing, and the bend head loss. So what is the surface area of the trash rack required? So you have to now, then this gives you the surface area of the trash rack required. So you give the vertical height and you get the trash rack width also. So you basically design the trash rack for the design discharge of 0.46 is given in this template. So you can change this, play with this, and do that. Similarly, for the orifice design, like I showed you, I worked out an example, but over here, basically, now you want to go to I think I use 0.6 sharp tested velocity through the orifice. How much you want to? I think I allowed 1.1. Okay, So in the formula, then Manning's coefficient 0.02 is basically stone masonry is 0.02 is okay. So then you have different Q sub 0.1 orifice height, height from the orifice. So these parameters you basically provide. What is the flood? And so I mean, if you provide so this, let's say this earlier it was I think I did it for 75. If you have a 75 cubic meter per second flood, what will be the blah blah? So this is already provided here. And now based on that, you basically get in the normal water condition, what is the difference in the, the calculation that I did in this one is done by this Excel file here, all these calculations. So it also shows you that I mentioned that we need a spillway length, because during the flood time, it diverts 1.36, okay? Q intake in terms of 1.369 is the, this one, like 1. Slightly because of some parameters, it must have been different. So it's basically diverts 1.38, but our requirement is only 1.46, okay? So we want to basically, so we need to know what is the length of the spillway. So this Excel sheet basically helps you to do the orifice design done here, okay? Provide the flood conditions here. What was the flood conditions? Everything was provided here, okay? And then it helped you to design. This calculation was done. It also did the design of the trash track and the design of the what is known as the spillway requirement in the length of the spillway required in the canal to pass the extra water. So please play with this and let me know if you have any questions. Maybe next class I can answer them and try to help them. I can provide you, if you want, I can provide you some, at the end of this, my lecture today, there are references given. So please have a look at those references. And it's available in the internet. You can search in the internet. If you want, I can send it to you also. Okay, so this was basically the exercise using template. I did not go into the detail, but I just wanted to cover that. Okay, now this was the intake. Okay, is there any? I know this is slightly technical, and I may have gone fast. But is there any question on the use of this template, or in the formula, or the objective of this design? Please let me know. Is there any question for now?
Colegas, haverá alguma pergunta da utilização desses instrumentos para cálculos? I don't think so, David. I think.
Okay, thank you. So, sorry, it's a little bit technical. So I'm sorry if I have been a little bit technical, but I wanted to give you a general idea of what goes on the design. And this is not detailed design. Detailed design is you have to look at the exact quantity of concrete, the steel, and everything. This one is basic feasibility level design that is necessary for feasibility level studies, so that you can get a good idea of the cost, basically, of the hydropower project. Okay, so now I want to just quickly go to the headdress part, and basically, when I mean by headdress, I basically mean the headdress basically means the canals, the pipes, and other conduits that takes water from the diversion point to the forebay. For large hydros, even tunnels, as I mentioned, are used. And basically, in the headdress, you want to make sure that the velocity is not too high. Because if the velocity is too high, the canal bed or pipe surface will be damaged. For earthen canals, it is only, you can maybe just bring it to 1 meter, 8.8 to 1 meter per second velocity. It should also not be too low because sediment will be deposited along the bed canal. After the settling basin, when the sediment is more or less ejected, it can be even higher than 0.4, but it should not be too low. You should provide adequate freeboard. You should avoid head loss seepage along the canal because you don't want to lose water. Rectangular, trapezoidal sections are normally used, and the alignment should be along stable grounds. I think these are standard thing. I don't want to think. And in terms of roughness coefficient and allowable maximum velocity, sorry, in terms of allowable maximum velocity, as I mentioned, for earthen channel, it is 0.8 to 1 for different clay with stone. And this is the Manning's N. 0.02 is clay with stone sand after aging. And these are Manning's N is the roughness of the surface, because the velocity will decrease when Manning's N is high, because velocity or discharge is indirectly proportionate to Manning's N. So if you use a masonry channel, the velocity can be as high as even 1.2. And if you have a cement sand mortar, a little bit lining, then you can even go higher. Okay. This is the canal. Concrete channel, you can go even up to 3 to 5 meter per second. Cement plaster, 3 to 5 meter per second. This is the canal when you have a line canal, for example. Okay. Sorry. Okay. So the channel cross section, normally it is rectangular or trapezoidal. And then basically the point is the design from a perspective. Basically, you want to make it more efficient. And the side, for trapezoidal channel, the side slope is important, okay? Because you have to have you cannot have very steep slope for loose sand. But if the sand, loose sand or thing, but if the soil condition is good, then you can have a more steep slope. Okay, so depending on the rock type, you can have 0.25 to 0.5, but whereas for a very light, loose thing, the horizontal should be 2. This is h to the power h to 1. Horizontal is 2 to vertical 1 to 3 to vertical 1. So, but for rock, you can have horizontal 0.25 to 1 to 0.5 to 1, because this is very stable, so that it doesn't create any erosion in the thing. And when you have clay soil, you have, this is in cutting and filling. When you say the canal is in cutting, then you cut. In filling means the current ground level is lower than the proposed bed level of the canal. So these are just design parameters. One thing you have to remember is this is also, I showed it earlier, it's a pipe hydraulic condition for a pipe flow and an open channel. Basically, in the channel, the velocity head is V1 is here, but the surface water is here, but the potential energy is surface water. Whereas in a pipe flow, it's under pressure, so the piezometric head is sort of is above the center of line of the pipe. So whereas the piezometric head in a water surface is the water surface, because this is at the atmospheric pressure. So this is basically, I think, the pipe flow and open channel flow, which is the principle used. And basically, for headrest canal design, you use this famous Manning's equation, which is applicable to uniform open channel flows, and basically it is velocity is given 1 upon n. N is the Manning's n, r is the hydraulic radius, and by hydraulic radius we mean the area of the weighted area, the area of the water, depth of the water and the channel divided by the weighted perimeter. Okay, so this is the hydraulic radius. S is the slope. Okay, this is the slope of the hydraulic slope. Sorry, the thing. And basically the channel is most efficient when it can pass the maximum discharge for a given flow area, roughness coefficient, and slope. So we want to make sure that we minimize the area for a given n and slope, because we want to reduce the cost of these conveyance system. So when the weighted perimeter, the contact of the water with the surface of the canal is minimum, you get the you get the most optimal solution. So for rectangular, normally the width is 2 times the depth. For triangular of 1 by 145 degree, this is if Z is given, then B becomes so this is the thing, and Z is side slope, and the side slope, and the Y depth is depth of water. B is the base width. So basically, for most efficient section for rectangular and trapezoidal, this is based on the hydraulic principle of which by minimizing the weighted perimeter, you would get the most efficient channel. So the typical Manning's N, again, I think I showed that again for different materials: clean, slain, earthen, 0.022, to natural riverbed, 0.024 to 0.05, and other soil conditions, river conditions, channel conditions, you have different things. And for basic criteria for canal design is the velocity should be 0.9 to 1.8 meter for unlined canals, because you don't want to do erosion, and then you don't want to make it too low also, so that there is no sedimentation. Freeboard is 0.3 meter plus 1/10 of the full supply depth, and the ratio of the curve to width of the canal is you want to bring it. You don't want to have an abrupt bend or changes, because that will also introduce losses. Okay, so the formula for all these for rectangular, trapezoidal, circular, parabolic is there. Hydraulic radius, hydraulic depth, section factor, other things are given. These are just used for thing. And again, I will introduce you to the Excel sheet again, where there is this, I did not go into the bottom intake. You can have a look. There's a headrest canal. So you have a stone masonry canal. Then you give the length of the canal. You give the freeboard. On the blue one, you give what is the thing. Then it will give you the for rectangular canal, what should be the, of course, sorry, it's a, you selected a rectangular, you selected a rectangular canal, but you could be a triangular, trapezoidal. If it's in the trapezoidal, you have another, thing, because there is some parameter is wrong, so it gives you a problem. But anyway, so this will give you the canal area. Is the velocity okay? Critical velocity should be, it says, to ensure stable inflow flow in a long canal, velocity should be 80% of the VC. So you should check this one, and based on this, you can do a canal design. And I will not go into the details right now, but I will encourage you to have a look at this template and look at the material I provided now. And based on this flow chart, you can design for a given discharge and for the given what do you call the upstream elevation, forebay elevation. Then you can design your canals there in this manner. So I would just, so this is the Excel template I talked about. Since we don't have so much of time, I will not go into each canal section, but I encourage you, as I mentioned, to have a look at this headdress canal template. And in the next class, let us discuss about it. Okay, so this is the Excel canal design using the template. For pipe design procedure, headdress canal is open surface. For pipe design is slightly, it's under pressure, no? Where pipes are, you can have a gravity open flow pipe thing also, but pipe flow is basically under low pressure. So basically, these are the design procedures. You know, you have, first you choose a standard pipe size based on availability. You make the velocity within this range. For HDP pipe, velocity is 2.5 to 3 meter, and the velocity is basically given by the discharge divided by area. And area is, once you know the diameter of the pipe, I mean, basically diameter of the pi r square is the area. So basically, since d by 2 is the r is d by 2, so it's 4 cube per pi. This is basically q divided by the area of the pipe. So basically, one important thing is the submergence head at the entrance of the pipe needs to be done. And because without, if you don't maintain a certain submergence head, then you will not, there would not be enough pressure for the water to enter the pipe. And calculate the head loss in the pipe length based on the, so you basically calculate the head loss based on the inlet, wall friction, bends, valves. So when the pipe bends through the walls, then you have the losses. The wall loss is given by the what is known as the Darcy-Weisbach equation, and which you can do it. And this is the formula used, and you can refer to standard technical books for the details about this equation. And basically, turbulent losses is basically based on the entrance coefficient, losses coefficient, bend, contraction, valve. When you have a bend, when you have a contraction, when you have a valve, there is a loss of head along the pipe. So basically, you check if the total head loss for design flow is less than the loss in head due to the pipe gradient S, and the profile is below the hydraulic headline everywhere. If not, repeat the calculation with larger diameter. Then you basically also determine the water level at the console structure at the allowed thing. Repeat the calculation of highest submergence due to flood flows. Excess water needs to be spilled at the end of the pipe. So this is the general procedure. It may be difficult for you to just, I'm going a little fast, go here. These are the coefficients for losses when you have a K entrance of this type is 1, this is 0.8. And when you have the R&D ratio, when you have a 20% bend, 45% bend, then you have basically, these are the K bend losses. This is the roughness values for different types of plants. The roughness for smooth HUP heat welded at site is 0.06, mild steel and other sources. Okay, these are parameters that are important. This is what is known as the Moody's diagram, which is very important. It gives you the friction factor in the Darcy-Weisbach equation to calculate the head wall loss, the friction loss on the pipe, and basically it is a factor of K upon D, and K is the roughness values for different types of pipes, and D is the diameter. Q upon D is the discharge over diameter. Then you get the friction value. So to calculate basically the friction losses in the pipes. So these are just to procedure. This is one exercise I provided in the presentation. Please have a look, and maybe because we are almost 11, I think now, so I don't want to take long. So I will just skip through this, but I want you to maybe in the next class, I will quickly go over it. Okay, so this is just there. So this is the pipe design flowchart I mentioned. And this is, I would now again encourage you to have a look at this template. Okay, the blue ones you need to fill, and the other ones are you already directly get from here. Okay, and basically these are provided here. So I will not go into detail now, but please have a look. And in the next class, we will, if you have any questions, we can discuss. So this was the pipe design exercise using Excel template. I want you to play with it and do that. So the next one is gravel trap with spillway, forebay and desilting basin design. So there is again Excel template given here. So I will request you to have a look at this settling basin design. It is slightly, this has got a few design concepts using Better's equation and other thing. And because if you click here, it gives you some comments on the parameters also. Some of the parameters, design flow, design discharge, you have to fill yourself. But the others calculation, it also shows you what is the calculation it is given. And basically, it will give you the size of it will basically give you the size of the length of the settling basin and the width of the settling basin. Okay, so basically it gives you that one, and it's automatically calculated here. I think I will stop here because it's a slightly quite a technical, rigorous design issue right now. So if you have any questions, I will be happy to answer them now. If not, I would request you to just go over the presentation material I provided today and the templates and the reference thing over here. I mean, some of these are not, I don't have soft copy. This is a hard copy. So this one, I can, maybe I will, these two guidelines, if I have not provided you again, I can provide you these references. I will upload it in our Dropbox and send you a link for these references, and you can have a look at it. I have followed this one, but the number 1 and number 4, I just have a hard copy of this thing at the soft, but 2 and 3, these are manuals that I have soft copies, and I can share with you.
Thank you. Can I have a question?
Yes, please. Yes, please.
I've seen that the file that Mr. Lucas shared with us is not the same that he used for the presentation. Is it possible that you send a new version?
Okay. Yeah. I will do that. Sorry. What I did was there were, I think, 1 or 2 slides. After I think I send you the thing. I will send you right now. Okay.
Okay. Great. Thank you.
Thank you so much. Yeah. Thank you for pointing out. I wanted to do that. I'll do that right now. Yeah.
I'd like also to make a question. If
Yes,
someone brings us already designed project and ask what is the key parameters that you may consider to evaluate the feasibility of the project?
Yeah.
Do we need to go to all of these parameters, or there is some key parameters that we can immediately find if it is viable or not?
Yeah. No, you're right. Actually, if the design or the feasibility study is already available, I think you basically need to go into the like I showed. I think this is important. I would really look at the hydrology of it. The install capacity and the energy calculation, no? The benefit, like this one. I would really look at the how this curve, power duration curve was calculated, number one, because this will give you the energy generation, no? Variation, number one. Then I would look at the design of different components, okay? The civil components, the electromechanical components, and the electrical components, and look at the cost estimate, okay? And when I mean cost estimate, I would look at the rates they used, okay? And some of the, I mean, there are some for civil design, I mean, you can make out the length of the canal, the size of the canal. No, there are, I mean, based using very simple thing, just to show that the design has been done correctly, you know, because sometimes if the design has not, you can get the cost, but if there is some changes in design, the cost may not change, but the project will fail, okay? So that you can do it during the detailed design also. So I would first look at the hydrology, the power generation, the cost, different components, then look at the cost benefit analysis. And any key and demand also, no? Because, okay, you generate this power, but what is the demand for it? Can all this power be consumed? But what is the demand for it? Can all this power be consumed? Sorry, I think there was an echo. So yeah, basically that would be the thing. Anyway, I will thank you. I think this is a very good question. I will, because we have this session, the review session after, like next class, I will look at the turbine selection, electromechanical selection also. Maybe I'll cover. And in the following class, we will do some, we have some sessions on evaluation of feasibility study. So basically, if the feasibility study is available, we will do some, what are the key steps for evaluation? We'll cover that also. And I will make sure that I'll try to, I mean, work with some of you, some colleagues from EDM, Funai, and Miriam, and see if there are some examples of feasibility studies where we can take the case study to evaluate the study. Yes, evaluate the project. Yeah, thank you. We'll cover this in our course during the evaluation. Today, I was trying to give you the technical sort of, I don't know how do you say that, the technical perspective of the feasibility study.
Okay, thank you much.
Sorry, there was some disturbance.
Ok, haverá mais alguma pergunta, colegas? Alguma dúvida? Well, Divas, I think there is no more questions.
Yeah.
Divas?
Yeah, thank you. Then let's stop now. I think it's past 11. And
Okay.
on Friday, I will see you at 9 o'clock again.
Thank you very much, Divas.
Thank you very much, Dr. Carlos. Yes, and thank you, everybody. Thank you. I mean, I hope maybe next time we should open our video of all participants also, so we can see your face. Yeah.
That would be good.
Yeah, I think we should do that next time. Yeah, I should have thought about it. Yeah. Thank you so much. Yeah.
Yeah. Okay.
Bye-bye. And
bye-bye.
I will send
Bom descanso, colegas. Sorry?
I will send the revised presentation because I.
Oh, yeah, it's important. Yes.
Actually, yeah, okay, thank you.
Yeah.